Hello, my name is Rob. I'm currently a postdoc at Caltech, and my supervisor actually is joining us. This is Joel Trop in the first row. So it's his first time ever seeing me speak in front of real people, which is pretty exciting. So hopefully I do a good job. I'll tell you about randomized methods for quantum many-body problems, and it's going to be a much more mathematical, numerical analysis type of talk that's really going to focus on some of these quantum Monte Carlo methods that have been alluded to by the previous speakers. So here's the plan. After a quick introduction, I'm going to go into a lot of detail for two examples. First, the quantum spin problem, and then the electronic structure problem. And my motivation with that part is actually to be able to communicate to mathematicians, what are the matrices that chemists are working with? What do they look like? What are the sparsity patterns? Why is it so terribly hard to get a ground state eigenvalue? And then I'll talk about two of these leading quantum Monte Carlo schemes. The first goes by this acronym FCIQMC, because it's really long to say. It's Full Configuration Interaction Quantum Monte Carlo. And I'll take you through a little bit of the derivation for why you might think it's a good idea and how it works and what are some of the alternatives. And then the last part of the talk is a pretty in-depth analysis of this variational Monte Carlo method, which is another QMC method that's currently in vogue. It's actually very popular. There's a lot of work going on developing it. So to introduce this topic, I would just say that ground state energies are needed for chemistry, and a lot of the previous speakers have communicated this much more clearly than I can as a mathematician, all of these important calculations about material properties that are built off of accurate ground state energy calculations. We want to get them, but it's so difficult to do so because you are going to have exponentially larger matrices as you increase the number of electrons in a molecule or the number of spins in a spin lattice. And working with exponentially huge matrices is, of course, hard. There are some promising results from this body of literature that I'll be telling you about, Quantum Monte Carlo, QMC. It's provided some accurate energies for systems of maybe 42 interacting electrons. That's benzene. There were some pretty accurate energies for benzene and slightly smaller bicyclobutane on the electronic side. And then for spin systems, people are routinely working with spin systems of 100, 200, 400, and I've seen 500 spins. Hence, a whole lot of different spin configurations. My motivation and the motivation of collaborators in looking at this area has been this belief we've got that QMC can be extended even further to bigger systems. But first, the sampling strategies, the optimization strategies that it employs maybe need to be touched up or improved. Maybe there are some things going on under the surface that aren't so great. And this is actually totally familiar to anyone who's actually implemented these methods, because it's pretty common you experience long convergence times. Maybe your algorithms are actually going to become unstable or converge to totally unreasonable solutions. So these methods, are potentially really powerful, but they're also finicky. And so hopefully, if we understand QMC mathematically, we can look at the problem and improve it. That's the dream, right? So this is the motivation for the talk. And I'll start out by telling you a little bit about the matrices involved. These matrices, they're discrete, they're really, really big, and in one paper by Alavi and co-authors, they're working with a matrix that they say is 10 to the 108 by 10 to the 108. So even storing a single vector of this size would be totally unmanageable. So you can't store a vector, much less manipulate the matrix. And before I tell you how we can deal with such large matrices, there's this question: how do they arise? What are the particular settings where you might run into such a large matrix? So here's an example that hasn't been treated by the past talks too much, but it's like the most basic quantum spin system. You're going to consider a transverse field Ising model, that's the name of this model, for spin 1/2 particles on a periodic 1D lattice. So this is an illustration of a periodic lattice. The nth spin is connected to the first spin, so everyone's got two neighbors. It's got a Hamiltonian that has two parts. And if you stare at it, you could see that the first part, you're summing over all the different neighboring spins. And what it's really doing is it's driving these spins to be ferromagnetically attracted to one another. So they all want to be aligned, they all want to be up together, or they all want to be down together in the spin Z basis. And then the second term is the transverse magnetic field, and that is driving all the spins to align with some external sigma x magnetism. So there's a competition between the first term and the second term. As you vary this h parameter, you can see either the first term winning or the second term winning, and there's a phase transition, which is pretty exciting to physicists. This is a 1D lattice, so it's exactly solved. There aren't solutions for 2D or higher, but for some 1D periodic lattices, there are exact solutions, and that's good because we can benchmark the accuracy of the methods I'll be talking about. Now, this is sort of a physicsy way to state the Hamiltonian, and it's not immediately clear to like mathematicians who are looking at this for the first time, how is this thing a matrix? So I'm going to take you through the matricization of this Hamiltonian, which I think like most of you know way better than me, but maybe some of my math collaborators who are going to watch this talk on YouTube have never seen before. So bear with me, it'll go pretty quick. So how do we do it? How do we represent H as a matrix? We're going to start by considering a tensor product wave function. So it's a tensor product of wave functions on the first, second, third, all the way to nth spin. These can either be spin up or spin down. And two simple examples, you might have up, down, up, down, up, down, up, down, or you might have up, up, down, down, up, down, down, up, down, down. And so there's a lot of possibilities. The tensor product wave functions form a complete orthonormal basis for this system, and the size is 2 to the n, where n's the number of spins. So the basis gets really large really fast. And then to represent H as a matrix, there's a wonderful tool called raising and lowering operators, where the sigma I plus, the raising operator on the ith spin, is just going to raise it from the down state to the up state. And the lowering operator, sigma I minus, is going to lower that ith spin from the up state to the minus state. And you can't go up and then go up again. You can't go down and then go down again. So sigma I plus is going to be sigma I minus, which is going to be 0. So these are the rules of these raising and lowering operators. They are linear operators on this basis. And if you work with these operators, you can finesse the Hamiltonian a little bit and just see that the second term, sigma ix, this Pauli operator, can be broken down into a raising operator plus a lowering operator. So this is cool because you're starting to see these simple linear operators that you can understand. You can understand their action on the basis set. And you can see the sparsity pattern of H by operating on the left and the right with basis vectors. So here, this might not be the standard terminology for spins, but it kind of connects to the electronic structure part later in the talk. I'm calling this first term the null excitation operator, and the second term the single excitation operator. And what I mean by this is we have 3 different cases here. If psi1 and psi2 are exactly the same as each other, right? They are the same in every single spin, then the null excitation operator is all that occurs. And so we've got to figure out kind of how are the spins aligned between all pairs of neighbors over the lattice, and that's going to give us our matrix element. Now, if they differ by 1 spin, I would call that like a single excitation. And then the null excitation operator would just be 0. The single excitation, that's what would show up, and you would get negative H. And then if you don't differ by 0 spins or 1 spin, you got to differ by 2 or more spins, and then you're just 0. So what this starts to kind of tell you is that the matrix H has n+1 non-zero entries per column. So there's 1 entry from the null excitations and n from the single excitations. And what does it look like? Well, it looks like this for 2 spins, or it looks like that for 3 spins. And these matrices are getting a lot larger. They're getting a lot sparser. It really would have been cool if I'd done 4 spins, but it starts to get too big to fit on the screen. And I kind of like looking at this. I mean, you can sort of see tensor product structure. Maybe in the off diagonals, there's like a diagonal of the off diagonal block. You start to get very cool like visual patterns. But probably the key takeaways for analysis would be, okay, it's getting huge. It's 2 to the n by 2 to the n. And then there's n plus 1 non-zero entries per column. So that's 3 non-zero entries on the left and 4 non-zero entries on the right. It's symmetric. It's real valued. So this is an example of a matrix. And blow it up to size 100 spins, 200 spins, 500 spins, and try to find the ground state eigenvalue. That's kind of a goal of quantum chemistry. Another situation, which was talked about by a lot of speakers, would be this electronic structure problem under the Born-Oppenheimer approximation. As I understand it, the Born-Oppenheimer approximation says we're just going to keep the nuclei fixed, and they're really heavy, they're not moving, but the electrons are orbiting super fast. And so we can try to figure out the structure of these electrons just holding fixed the nuclei. There is a kinetic energy term, and then there is a term that's the attraction between the electrons and the protons, and then there's a term that's the repulsion between the different electrons. And I'm not going to spend too much time on this. It's been discussed a lot, but it's totally incomplete. This is not the whole model, right? Because there's 2 other things that are going on to actually turn this into a discrete eigenvalue problem. And the first would be spin up and spin down. Each of these electrons is associated with a spin up or a spin down state. And then there's the Pauli exclusion principle, which says that like the physical wave functions, the ones that we care about, have this crazy anti-symmetry property, which says that if you swap the position and spin of electron I and the position and spin of electron J, then the wave function switches sign. You get out the negative wave function. And so you can't have 2 electrons that have exactly the same position and spin, but you can have 2 electrons that have exactly the same position and opposite spins. So that's sort of nuts. Quantum mechanics is nuts. And I've asked my collaborators, like, how do you think about such things? How do you find this at all intuitive? And they say we just get used to it over time. We don't actually have an intuition. This is Tim Birkelbach, if any of you know him. This was his answer for me. Maybe y'all have better intuition than me. So how do we represent this as a matrix? This one is harder than the quantum spin case, but we'll start by looking at a single electron. Just like we started by looking at a single spin, before we took these tensor products, we're going to have to do a little more work. So first, you take a spatial orbital, and you expand it by coupling it with a spin up or a spin down to get what are called spin orbitals. So you've grown your basis from m orthonormal single electron spatial orbitals to a bigger set of orthonormal spin orbitals. And the next thing you do, which is really beautiful and surprising, is introduce the basis of Slater determinants. So these are a lot of tensor products, but they're all put into linear combination in such a way that it satisfies the anti-symmetry property. And the notation here, I'm basically following this textbook, which is really good, by Sabo and Ostland, where there's I, J, all the way to K. And what that's denoting is the diagonal elements. The spin orbitals that show up in the diagonal are going to be I, J, all the way to K. Because if you know the diagonal with these Slater determinants, you could figure out all the other entries, because it's just like the first row is the first electron, the second row is the second electron, all the way to the nth row is the nth electron. The first column is the ith orbital, the second column is the jth orbital, all the way to the kth orbital. So Why are these great? Because they automatically satisfy this anti-symmetry property. If you exchange two columns of a determinant, you swap signs. And that's exactly what we need to encode. Slater determinants form an incomplete orthonormal basis because you don't have all the spatial orbitals to fill out all the possible orbitals that could exist. And it's really, really big. It's size 2m, choose n. And think of like 50 or 100 orbitals. Think of like 20 or 30 electrons. And if you want to actually compute such large combinatorics, you could do it on Wolfram alpha. And it'll always give you like the exact answer, which is kind of cool, as well as it'll tell you whether it's 10 to the 25 or 10 to the 50 or 10 to the 100. So big basis. And then again, we can introduce the raising and lowering operators. So this time, I'll denote them with AI plus and AI minus. The raising operator is going to create an ith orbital if I is not yet occupied. And the lowering operator is just going to annihilate that ith orbital. And again, we insist that you can't raise twice, and you can't lower twice. This is a little bit more intellectually confusing, perhaps, because you started with n electrons, but then this would be n plus 1 electrons. But the math works out perfectly in the end. And one could think of some extended Fock space where you could have any number of electrons, which is a nice framework. So if you do a lot of work, like 10 pages of work in Sabo and Ostland, you get to this matrix representation of H, which says that there's two terms, and the first one is going to be composed of a single raising operator and lowering operator. The second is going to be composed of two raising operators and two lowering operators. And the summations will run over your entire basis of spin orbitals. These are integrals, these coefficients, which are just denoted using this standard format, IHJ and IJKL. The first would be an integral over one electron position, so it's a 3D integral. The second would be an integral over two electron positions, so it's a 6D integral. And I believe it's pretty technical, but if you choose the right basis sets, there are programs like PySCF that will compute these really, really fast. So that's more technical than I understand. Yep? Oh, yes. So I really never specified that, did I? It takes into account the kinetic energy term and then the attraction between the electrons and the protons. It's parts of the Hamiltonian, right? Everything except for the repulsion between the electrons.
It's just because you used H earlier as a constant. So
oh, yeah, thanks. I'm sorry. It's a long tutorial, so I might double use notation.
Right, so that's a operator. That's what I'm...
Yeah, it is. It is. I'm kind of trying to hide the details of what these coefficients are because I'm mainly trying to just show you the sparsity pattern. Like, that's the goal. Yes?
So what's the smallest you can choose K? Like, what's the smallest number of orbitals you can have given the number of electrons in the system? Because if you make it equal, like half the number of electrons, then you don't have any space for excited state, right? So.
Oh, gosh. So this is a little outside my ken. Most of the times you run into FCI matrices would be post-Hartree-Fock calculations. And I believe Hartree-Fock, you need at least the number of orbitals that you've got electrons. So that's what you show up with in practice. And that would be the number of spatial orbitals would be the same as the electrons in Hartree-Fock. Is that right, guys?
You can have a feeling that's over 1/2, but indeed, the feeling can never exceed 1.
Yeah. So, when you actually want accuracy, think about like 80 orbitals and 20 electrons, something like this, right? But, the picking of the orbitals is really, really a fine art and science. And it's an amazing body of literature, actually, but maybe too technical. So again, we can see the sparsity pattern by operating on the left and right with basis vectors.
I think just maybe one thing along that line is that as you approach the complete basis limit, which is you're supposed to solve in the first place, to solve the many-body Schrodinger equation, the number of orbitals keeps increasing, but the number of electrons is a physical
Ideally, you
number.
would have an infinite number of orbitals.
Ideally, that's right.
Yeah.
But you can have how many orbitals as you want, because it is the solution of a field theory. So you can have a complete basis set with how many orbitals you want. What is important is how many excitation you have here. So you have to make a distinction between the basis and how many excitation you have in this system. And the point is that if you look to the structure of that Hamiltonian, maybe you will say you conserve and you preserve the number of excitation that you have.
That's right.
This is the meaning. You have how many? You have an infinite countable number of orbitals. That is your basis set in your Fock space, and then you count the number. Or better, is the set of creation annihilation operator that you have, and then the number of the Fock space is fixed by the number of total excitation that you have. I will refer to it in my tutorial tomorrow.
Good, good. So then maybe I don't have to do it here. That's very convenient. No, this is awesome. We're supposed to be engaged, right? So you can look at this and you can figure out the sparsity pattern. So double excitations means that you have two orbitals that are different. So we have ij on the left and kl on the right. And if you evaluate what's going on, you can see this coefficient. Single excitations means that you have just one orbital difference. So I on the left and j on the right. And then these would be the coefficients in your matrix. And then null excitations, you're operating by the same vector on the left and the right. And it's a little more complicated. But what's important here is the sparsity pattern, actually, because as you go to big systems, that's what's going to really drive the cost. And the sparsity is completely determined by these double excitations, because there's just so many of them, right? There's order n squared times n squared double excitations that could show up. So, the single excitations, maybe the coefficients look a little more complicated. The null excitations, maybe it looks the most complicated. But this is the scaling that's really determining the sparsity pattern of the matrix. So we've got two big matrices. And whatever shall we do? Well, I'll start by traditional methods and then go to the FCIQMC method and then VMC. And I'm doing awesome. It's 9:24. Okay, this is going to be about right. So for small matrices, there are iterative eigenvalue solvers that work great. And so the simplest, oldest one would be the power method. Subspace iteration expands on the power method to give you multiple eigenvalues and eigenvectors. Landshos algorithm is really good for symmetric matrices. It's a Krylov-based method. Jacobi-Davidson, which some mathematicians aren't so familiar with, it leads to fabulous results in this case. But I'll focus on the simplest one because that's actually the most amenable to randomization. So that would be the power method. It's the simplest method for finding the maximum modulus eigenvalue of a matrix. We're going to deal with symmetric matrices, so that means like the biggest magnitude positive or minus or negative eigenvalue, whichever one has the biggest magnitude. Power method looks like this. You iterate 1, 2, 1, 2, 1, 2, 1, 2. So first you perform a matrix vector multiplication. Xt plus 1 is axt. And then you normalize. Xt plus 1 is xt plus 1 divided by its norm. So that gives you a norm 1 vector. It kind of stabilizes the size. There's various options for step 2, but step 1 is what's going to drive you toward the maximum magnitude eigenvalue, eigenvector pair. There are a couple eigenvalue estimators, actually, that you can find if you look way back in the literature to like the 1950s. There was a historical eigenvalue estimator, which maybe you haven't seen anymore, where you look at axt and take the inner product with your starting iterate, or basically with any fixed vector, but your starting iterate is already like a good guess, so that's a good place to look. You take the inner product of axt with your starting iterate divided by the inner product of xt with your starting iterate, and that'll give you an eigenvalue estimate. And then it's like you're using x0 as your test vector, but why not use xt as your test vector? Wouldn't that be better? And that's what modern power method implementations would use. They would use this particular Rayleigh quotient form to estimate what is the eigenvalue at each stage of the game. Here's the first math result. There will be several in this talk, so bear with me, or if you like this sort of thing, then I'm really happy to go into the details. The power method converges pretty nicely, depending on a relative spectral gap. So I've written this all out with all the details. We have a symmetric matrix A of size n by n, and the largest magnitude eigenvalues, for now we're going to denote lambda 1, lambda 2, et cetera, associated eigenvectors v1, v2. And then this R that shows up is a relative eigenvalue gap, so it's hopefully less than 1, hopefully substantially less than 1, right? The second highest magnitude is going to hopefully be some small fraction of the highest magnitude, because that's going to drive the convergence. And then what might be a little more unfamiliar is I'm introducing the acute angle between two vectors, which would be denoted the angle between x0, your starting iterate, and v1, the maximum magnitude eigenvector. And that's defined as the arc cosine between, oh, that's actually a typo. It should be the absolute value of the inner product x0, v1 divided by these norms. Okay, so it's the arc cosine of this absolute value. It's going to give you an angle between 0 and pi over 2. Now, the eigenvector estimates are going to get closer and closer to the true leading eigenvector if R is less than 1 and tan theta is finite. And they're going to do so exponentially fast. So that's good. The angle is closing between these two vectors over time. And the historical and modern eigenvalue estimates are going to also converge exponentially. And the modern one's way better, because it converges at a rate r to the 2t, whereas the historical one would converge at a rate r to the t. And why am I telling you about some weird historical eigenvalue estimator? Well, it's the one that's going to be used in FCIQMC. So just to be clear, some of the oldest methods have been the ones that have been most amenable to randomization. Maybe because they were really simple, maybe. So this is the convergence of the power method. Yeah, for sure. Let's see, what would change? I actually think that this would change, potentially, where you might need a denominator term that looks like 1 minus r to the 2t tan squared theta. And apart from that, nothing would change. To get rid of the denominator term, this uses the fact that this, no, that's always going to, oh, never mind. Yeah, it's exactly the same. Joel's right. Okay. Yeah, Joel's right. This is going to be exactly the same for a non-symmetric matrix. A complex remission. That's right. Oh, right, because you are using the orthonormal decomposition right from the get-go. That's right. So sorry for my flubbering. We believe that this holds for any Hermitian matrix. This is what we believe. Yes. 95% confidence. I derived it by hand yesterday for symmetric matrices, so I know it's right for that. Yeah, so you can use this for small systems. Apply the power method to A equals I minus epsilon h for small enough epsilon. And you need small enough epsilon so you're sure that your ground state eigenvalue becomes the biggest magnitude eigenvalue of A. That's what you need. But the problem when you try to extend this to bigger systems is the power method is going to densify fast, right? You know, you start with maybe a sparse iterate, but then it's like, okay, now there's n squared m squared, non-zero entries. Now it's n to the fourth, m to the fourth, n to the sixth, m to the sixth, and so on. I mean, it gets really dense. So how can we adapt the power method to larger matrices? This is maybe a natural question, and it's one that's been answered in a couple different ways. Full configuration interaction quantum Monte Carlo is one way to answer this question. And it's really inventive. I mean, I just think it's really cool because it introduces these random walkers, like, it's sort of a fanciful idea to create an interacting particle system, you know, to solve a discrete eigenvalue problem. It's very creative, it's very evocative, it's very fun, actually. It was originally conceived back in the 1950s by von Neumann. He created such an approach to inverting a matrix back when he was playing around with the first computer, the ENIAC, at Los Alamos National Lab. He came up with a way to invert a matrix using random signed walkers. And I don't think Alavi and co-authors were necessarily thinking of von Neumann's approach to inverting a matrix when they came up with this, but you know, they're pretty similar. Maybe it's a very natural idea that's occurred to many people over time. They interact in a game of birth, death, and annihilation, which was just a fabulous name for a paper that introduced this method to the world. Birth means that for each walker who is currently occupying J, this index J, you're gonna, with some probability pjk, spawn a random number of particles at a new location k. And what is the random number of particles? Well, it's going to be defined by the greatest integer that's less than or equal to the magnitude ajk divided by the selection probability pjk plus a uniform random variable. And this is a fancy math way of writing the fact that we want a random variable that takes ajk over pjk and rounds it up or down to the nearest integer with the correct probabilities such that the expectation is the magnitude ajk over pjk. Right? So adding the uniform random variable and then taking the floor function is a way to accomplish that, like in your code, for example. The walkers carry signs. And the signs are going to stay the same if ajk is greater than 0. And they're going to be flipped if ajk is less than 0. So negative entries in A are going to flip the signs of the parents. Death is the way of representing the diagonal entries of the matrix, which are usually going to be pretty small, like less than 1. They're going to be like 0.8 or 0.7 or something. You're going to have walkers that are dying off. But in complete generality, what you might want to do is replace your walker that's at position j with njj walkers, where njj is a random number with mean magnitude ajj. The walkers that are replacing this parent are going to have the same sign as the parent if ajj is positive, which almost always happens. They're going to have the opposite sign of the parent if ajj, sorry, typo, is less than 0. And annihilation means that you cancel the walkers on the same site with opposite signs. So maybe it's a lot. I don't know if you haven't seen it before. What's up? Oh, a particle is a walker. And I meant to change everything that said particle to walker. In the interacting particle system literature, they're kind of used synonymously. Yes?
How do you pick pjk?
With a lot of development and refinement over the years. So, you know, there's some idea mathematically that you do the best if pjk is proportional to ajk. But the way this works programmatically is you pick a site and then you evaluate what is the AJK on that site, right? So you don't know a priori what is AJK. You surely can't define your probabilities just by looking at all the different sites and then forming the probabilities proportionally. So folks kind of try to guess about what's the magnitude of the different sites using some elaborate schemes where first you're going to choose a single excitation or a double excitation, and then maybe you're going to look over all the symmetry allowed excitations, and it ends up being some sort of mix between importance sampling and choosing uniform at random that are combined in elegant combinations. But you could think of various ways, yes?
Do you have any motivation or intuition behind the algorithm?
Well, let me give you the next slide, and then you'll tell me whether I do. So FCIQMC approximates a matrix multiplication. That's what it approximates. It approximates a matrix multiplication in the sense that we can introduce some vectors, xt plus 1 and xt, where xt is the sum of the signed delta functions on the walkers, and xt plus 1 is the sum of the signed delta functions on the walkers after the time step's over, after you've birthed, deathed, and annihilated. And you get this expectation working out perfectly. So it is, in expectation, working out what is the matrix vector multiplication. It's doing this without forcing you to actually evaluate all the columns of A that you would need to evaluate if you did this deterministically. And we can even break it down to a micro scale and say that the birth step is performing multiplication with the off diagonals. The death step is performing multiplication with the diagonals. And the annihilation step is performing the addition. A is the sum of the diagonal part and the off diagonal part. So, hopefully that sort of helps. I find that this expectation, is really important. One thing that's annoying, really annoying though, is like, are birth, death, and annihilation going to stabilize the population over time? Is it going to grow bigger? Is it going to grow smaller? And my subjective interpretation is that this is a little bit of a mess. Because you have these random dynamics. And so at the very best, you would expect some pretty big random fluctuations. You've got to stabilize it based on the amount of available computational resources. Alavi and co-authors introduced this idea of an adaptive shift. So instead of just defining A is identity minus epsilon Hamiltonian matrix, now you've got H minus delta Ti, where delta T is going to control the amount of death that takes place, right? And it gets adjusted at every iteration or every 10th iteration or 100th iteration. So if you have a growing walker population, you'll increase the death. And if you have a shrinking walker population, you will decrease the death. This, I would expect, would still lead to quite a lot of random variation. And you would only want to turn it on after you've reached a target walker population. So they would grow a whole lot at first, and then you would try to stabilize them. That's the idea for just controlling the resources during this operation. Does it?
Stabilizing value of delta T constants related to your eigenvalue? Or?
Yeah, that's right. So they try to back out an alternative eigenvalue estimate. I haven't shown you the main eigenvalue estimate, but that'll come on the next slide. And they try to say there's actually two, and one of them is based on delta T. Yeah, delta T in some sense is how big is it growing, it's how big is the eigenvalue. That's absolutely right. But if you really want to estimate the eigenvalue, you ought to do what I'll propose on the next slide. Delta T would be an inferior eigenvalue estimate in terms of accuracy. Does this converge? So that's a question that doesn't actually get asked very much. Like, you get pretty good empirical results. And in some sense, they sort of justify it. But like, why mathematically would we expect this to converge, and in what sense would it converge? what are the eigenvalue estimates? What are the eigenvector estimates? What do they converge to, right? And so maybe a little bit of care or thought about these issues would be something that, could lead to some, modifications of the scheme or maybe ways to stabilize it. So if you look at all the walkers and you look at their signs and you look at the shift, it is Markovian, right? Which means that if you know the value of this stuff at time t, you can evolve the system forward to time t plus 1. You don't need to look back to any previous information. You could just erase that from memory. Markov processes like this sort of generically converge to a stationary measure. You might hope that this is the case for this particular Markovian system, and you might anticipate it being so, because the empirical results look like it's converging. Moreover, you might hope that under this stationary measure mu, the expectation value of x, which is your sum of signed delta functions on your walkers, your representation of the ground state eigenvector, you might hope that it lies close to the true ground state, right? So this, in general, will be a very dense vector, this expectation value, because it's the average over many, 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 many sparse vectors that could exist, and it is dense. And you might hope that it's really close to the ground state eigenvector. Yes, question?
Yeah, it's a rather naive question, so I cannot get any intuition about the third point, that how we expect it to lie close to ground state. So, I mean, how, at least from physics point of view, I think we have stationary kind of phases that they are far from ground state, but maybe, I'm missing something here.
So my motivation has been that this is a stochastic version of the power method. The power method converges to the ground state. So we would hope that the stochastic method kind of sticks close to the deterministic method. And therefore, it too is pretty close to the ground state. So that's the hope. Each one of these steps is performing a matrix multiplication. Each of the matrix multiplications is going to drive you closer to the ground state in expectation. So, you might hope that you're getting closer and closer over time. There's also stochastic noise that drives you away from it, though. So that's sort of the hope. I hope that that's helpful.
Because we do not have any, how we can be sure that there would not be any stochastic resonances? Possibly between the BAS and our system, which can kind of make it radically different.
Well, I'm posing this as a question, and I'm using language like we anticipate.
Okay.
So really what I'm suggesting with this slide is if there's some intrepid mathematician who would like to prove that this algorithm actually converges, I regard it as quite open. So that's what I'm suggesting. You asked about x0, which is a really good question. When you've got a stationary Markov process, you can look at it under the stationary measure, and it's going to be the same at time 0, 1, 2, 3. People even extend it back in time to time -1, -2, -3. And that's what stationary measure means, really. It means it stays put. Yeah. So this is just a stochastic average of any particular time of this Markov process if you started it, if you initialized it from mu. And we don't initialize it from mu. We initialize it from some guesstimate of the ground state. Now, yes, tell me.
Ground state, because this gives the highest eigenvalue at a world
of A, which is a identity minus epsilon h. Yeah, so it's this particular shifting of the eigenvalues that changes it from being the smallest real one to the maximum magnitude one.
Yes, thank you. And I have another question.
Yes.
And the slide that you discussed before with the theorem and the results of the equation on the symmetric matrix. You had information on the second highest eigenvalue. Do you get this as well with this Monte Carlo? random method, or do you only get the highest eigenvalue?
Oh man. So firstly, what I showed previously was a convergence rate. There are no convergence rates for FCIQMC. You might sort of hope that it follows the power iteration. And so it's got a similar convergence rate. From the plots I'll show you later, that's not quite true. It gets really stochastic. It kind of saturates at a certain error level. Then you asked about whether you can get out the low-lying excited states. I'd regard that as kind of current research. How can you extend this? You sort of can. You can do a version of subspace iteration. With collaborators, I actually recently came out with a paper this week that discusses how one could do such a thing. Well, to archive. We put it to archive again and resubmitted it. And hopefully it'll be in publication soon. Yeah. Another question? Oh, yeah, subspace iteration. Yeah, it's tricky, and I'm actually going to talk about it in workshop 4. So this talk, for simplicity and tutorialness, is limited to the ground state. Of course, we want to know the low-lying excited states. And that's really fun, but it just gets a little more complicated. And so in workshop 4, I will give a talk that's like the version of all this stuff for excited states. Yeah.
Okay, so how would you combine a eigenvalue preconditioner within this method? Is it as simple as the power method? To isolate the eigenvalue of interest.
There have been papers by Lavi and co-authors that have almost that title, like a preconditioned FCIQMC. I don't know how they do it. So the answer to your question is actually I'm not quite sure. But preconditioners can be very powerful, and so it's a natural idea. Yeah. So, all right. I'm actually more of an expert on variational Monte Carlo, which is the second part of the talk. So, all right, let's say you're close to the ground state, optimistically. It makes sense then to estimate the ground state energy using this historical estimator, which in this case turns out to be the ratio of convergent averages of a Markov chain. And the convergence rate in this case is going to be t to the negative a half in distribution, or it's going to be very slightly slower if you look at it in an almost sure sense. Generically, Markov chain Monte Carlo schemes give you empirical averages that converge at a rate t to the negative a half. When you take the ratio of two such averages, you could see, for example, by a power series expansion that it's also going to be t to the negative a half. And that lines up very well with the empirical results. This is all complicated, though. I do want to introduce one alternative.
And this is better than putting this sum outside the ratio?
Oh, yes. Miles. Yeah, miles better. Empirically, and then also, I wouldn't know how to derive a convergence rate if you put the sum outside the ratio. But maybe other folks would. Why not approximate this more directly? That's the last question I'm going to raise about FCIQMC before moving on to VMC. And you can do it. You can introduce what would be called a random compression operator, phi. And this takes a d vector and spits out a d vector that's pretty sparse. So it has at most m non-zero entries, where m could be like 1,000 or 1,000,000 or whatever you can afford. And then it's equal to the original vector in expectation. And then if you've got such a compression operator, there's this technique which was proposed by my PhD advisor, Jonathan Weir, who's at Courant, in 2017, which nowadays they're calling FCIFRI, full configuration interaction fast randomized iteration, where you take a much more direct spin off of the power method. Before doing the matvec, the matrix vector multiplication, you sparsify. So therefore, it becomes much cheaper. And so you can iterate 1, 2, 1, 2, 1, 2. And exactly as before, you can approximate the dominant eigenvalue of A using this historical eigenvalue estimator, which again is going to be the ratio of trajectory averages of a Markov process that ideally converges, and you get a t to the negative a half convergence rate. The question then would just be, how do you choose the random compression operator? What's a good way to do so? How do we do it? How do we do it? And I had a nice result. I thought it was a nice result that shows what is the optimal way to do this. And it's basically what you would expect, but we'll see if there are any surprises as I reveal the next items. So you've got a vector, x, it's a d vector, and just let alpha be a permutation that orders it from the biggest magnitude to the smallest magnitude. Then I ask, what is the best compression operator? What is the best way to sparsify a vector so that the mean squared magnitude of the perturbation is as small as possible, subject to unbiasedness and sparsity constraints, which are our definition of a compression operator. So the first thing you do is you keep the largest magnitude entries exactly. You don't perturb them at all. You just keep them as they were. The top k ones stay exactly the same. And the second thing you do is you randomly perturb the smallest magnitude entries. You do it in such a way that either you're taking xi and you're raising it to a bigger magnitude while keeping the same sign. So xi goes in, xi over pi comes out with probability pi, or you're just setting it equal to 0. So you're multiplying it by something that makes it 0 or makes it big. And here's the particular pi's you use. They're proportional to the magnitude xi. And choose k as small as possible while ensuring that all these probabilities in step B are less than or equal to 1. So this gives you a pretty good formula for the best way to sparsify a vector. And the schemes that John Weir, my advisor, has advocated and implemented do this. They do this FCIFRI. Here's a picture from one of the papers. And it's a cool picture. It's a result for neon, which is kind of small in terms of FCI calculations. It's only got 8 electrons and 22 orbitals after accounting for the 2 frozen core electrons. And what you're seeing is 95% ranges of variation in the stochastic eigenvalue estimates. Particularly, what they're doing is they're backing out from the eigenvalues of A. What are the eigenvalues of the Hamiltonian? They're looking at how far they are away from the real ground state in millihartries. And if you're making things really sparse, it's pretty noisy. If you're allowing some more non-zero elements, it gets better. And if you're allowing a lot of non-zero elements, it gets better still. And you see, if you really squint at this, that yes, there's a t to the -1/2 convergence profile. I raise this, this is a tutorial. I raise this not so much to like advocate our group's work, but just because I think it's maybe a simpler way to think about what's going on in these stochastic power method schemes. FCIFRI has a little bit of a simpler structure. Here's this same picture, and I'm going to give you some limitations, both of FCIQMC and FCIFRI. Now, FCIFRI is going to be way more accurate than FCIQMC, but FCIQMC is going to be way cheaper than FCIFRI because you don't have to look up as many entries in FCIQMC. But if you look at the literature over the past 10 years, you can sort of see elements of FCIQMC and FCIFRI all being combined together, right? So people really want to improve the accuracy, so they make it less stochastic. There's things like an initiator approximation. People use a lot of importance sampling. Maybe they look up a couple different off-diagonal entries. You sort of see these ideas being mixed together to try to get the benefits of both worlds. There is not a mathematical understanding of when these methods succeed versus fail. And that's probably the biggest open question, I think. Establishing geometric ergodicity in the abstract isn't so good, but like knowing from a nuts and bolts perspective, like what are the matrix properties that lead these methods to do good versus not perform so well is of big, big practical relevance. I have some ideas that it's related to diagonal dominance, but I'm kind of stumped. And so let's see. I've got 20 minutes to do VMC. But are there any questions about this first?
You mentioned that the historical estimate is kind of easier to randomize. So can you quickly explain why it is used as compared to like the other one?
This would be a trajectory average of a fixed functional of a Markov chain. And that's exactly what you would always try to get from a Markov chain-based method. The convergence is pretty well understood. If you were to put XS right there, you would have a variational estimator that's always too high, that really penalizes you for a lot of the discrepancies from the ground state. I feel like I'm not explaining this that great, but empirically, this is going to be by far the best. It's amenable to a convergence analysis. We've tried all of them. And so maybe the simplest way is just to say that, OK, it's a trajectory average of a Markov chain with a fixed functional. And that's normally what we do with Markov chains, and that's what we would expect to converge nicely. Great. Yeah. So in interest of time, I'm going to go a little fast through VMC. I mean, VMC is really fun, and it's in vogue. So I wish I had more time. But I think FCIQMC is just so mysterious, right, that like everyone wants to know more about it, which is cool. Yes?
I just have a quick question. So just to connect to the beginning of the talk, talking about the quantum Monte Carlo for the Hamiltonian.
Yes.
So is this essentially a way of selecting the different determinants that you're going to take into averaging?
Yeah, for sure, for sure. And so that's how they pick the P's, the off-diagonal probabilities of selection, is like first you randomly choose whether you want a single or double excitation. And then you maybe like consider what are the symmetry allowed double excitations. And yes, indeed, yes. Yeah, that's right. That's right. So the ground state, you know, it solves an eigenvalue problem with lambda as small as possible, but there's also an immensely powerful variational principle, which says the ground state wave function is the function that's going to minimize an energy functional, which is the Rayleigh quotient involving the Hamiltonian H. Variational Monte Carlo essentially takes this idea and runs with it. It is going to minimize this energy functional over a parametrized wave function class, psi theta, where theta is a vector of real or complex valued parameters. And it just does this iteratively with a little bit of Monte Carlo sampling thrown in. So you start by sampling from the wave function density, and then you're going to use the random samples in a way that I'll describe in more detail on subsequent slides to estimate the energy gradient and potentially other quantities that you need for the optimization. You use that information to update the theta parameters, hopefully to get to lower energies. And for the example that I'll really go into, we're going to move back to the quantum spin systems. We're going to move back to this transverse field Ising model. And we'll attack it using a parametrized wave function that's been very successful for this system, which would be called a restricted Boltzmann machine. And so this was proposed by Carleo Giuseppe, and they have a whole software suite that implements such sorts of ansatzes. They've studied a lot of quantum spin problems. And in particular, this would be a two-layer neural net. And so there have been generalizations to multi-layer neural nets. It's a little different from the ansatzes that are being used for the electronic structure problem. So don't try to draw any parallels there. The electronic structure problem, you really got to work hard at your ansatz. It's really tough. I know Lynn's group has been working on it for a while and made some progress, but it's like a whole talk, I'm sure. This one's a little bit simpler. You have a certain number of features denoted by alpha. So like by improving alpha, you get a more expressive ansatz. I usually use alpha equals 5. You could use alphas 10, 20. It gets more expensive, though. Then there's a product over all the translation operators on the lattice, these operators that shift you 1 to the right, or 1 to the left, or 2 to the right, or 3 to the right, or 4 to the right. And then for the nonlinearity, we're going to use a cosh acting on a affine function of translated spins with weights W and biases B. So this is a pretty standard thing in neural nets. You take some affine functions of your input space, apply a nonlinearity, and this is a way to bake in the translational symmetry really, really naturally. And these are going to be complex valued, which is kind of cool, and which works better than real valued parameters. It's more expressive, and I'll show you the math of how to do the optimization. Optimistically, this is what you get out. So you see in orange the VMC estimates, and you can't quite see what's happening at iteration 0 because it's way, way off screen. The energy estimate would start at like 0 or something, and then it would just go down. It would decrease and improve, get closer and closer to this true ground state, which is exactly known. And then there's this other thing going on, too, in this plot, which is really weird, which is that the variance in the energies also decreases. So you wouldn't expect that for most stochastic optimization algorithms. You wouldn't expect the variance to get better over time. Rather, you would expect that it's pretty constant and you have to do a lot of averaging. But in VMC, you get better results. The variance, the wiggles, are actually shrinking quite a lot at about iteration 500. This is because of what's called the vanishing variance principle or zero variance principle, a special feature of VMC, proved a little later. Now, how do we update the theta parameters? Like, that's the big question. How do we actually do it? What are the nuts and bolts of this algorithm? So, yeah, for sure.
Why for this particular model, within 100 iterations or so, the variance is already like 10 to minus 6? Because if you look at the y-axis, even when you think it is big, it is still extremely small, right? Well,
yeah. Well, good ansatz, tons of data, and a really fast optimizer. So, you know, the goals of this talk are maybe to shine light on what these methods look like when they're performing great, and then also to raise doubts about these methods, whether they always perform great, or whether there's big outstanding questions. And both are true here. I mean, you know, these are real results. I did not cook this. I, you know, did all the coding myself, and it worked for this system. But, you know, use a slightly different Hamiltonian, go to 2D, you start to run into more interesting convergence, slower convergence, energy spikes and such things. Yeah. I'll take you through a few optimizers and maybe a little bit of derivatives, which you need for the optimizers. So the way to get derivatives, I believe this is absolutely the cleanest way to get derivatives. And it's not too common that people do it this way, but I'm trying to maybe convince you all, and then you all can tell a friend, and they could tell a friend. You've got to fix the vectors of parameters theta and consider a little update. So you're moving to theta plus delta. Then don't look at the wave function. Look at the intermediate normalized wave function. This is the key point. The intermediate normalized wave function is the wave function that's just been multiplied by some constant to fix the inner product with psi theta. So it provides just a little bit of normalization, which just makes the gradients and Hessians much cleaner. So specifically, once you've done this, you could take a generic Taylor series expansion. You know, if the original function is nice and differentiable with respect to theta, so is this intermediate normalized wave function. And so you get out the 0th order terms, some 1st order terms, some 2nd order terms. You can see that the derivatives of this intermediate normalized wave function are almost the same as the derivatives of the unnormalized wave function, except you've got an offset by some multiple of the wave function itself. And I've indicated that the second derivatives are just dot, dot, dot. You can get formulas. It's going to be a linear combination of 1st, 2nd, and 3rd derivatives. No, 0th, 1st, and 2nd derivatives, thank you. But we don't need it, and it gets complicated fast. So if you do this, if you just plug in this intermediate normalized wave function with its second order Taylor expansion and move terms around, you get out something rather nice, where the energy difference is being expressed to second order accuracy with exactly the sort of things that you expect and want, like very clean Rayleigh quotient formulations of what are these gradient and Hessian terms. In the gradient, you get what you would expect. You get one first derivative. In the Hessian, there's two terms, and the first one's got a first derivative with respect to I on the left and a first derivative with respect to j on the right. The second has a second derivative with respect to ij on the left and the wave function on the right. They're all Rayleigh quotients, and the only thing that you got to do to make this perfect is introduce h hat, which is h with the energy offset. Just that one little normalization helps you to get these very clean formulas, which I think are nicer than what you would see in like works by Sorella or like the main textbooks that derive such things. They're sort of intuitive from a mathematical perspective because of all the normalizations we've done. So there's takeaways from this. I mean, I'm not taking you through laborious mathematical derivations without a point. If you've got real theta, the gradient's going to be 2g. The Hessian's going to be 2h plus 2j. If you have real valued parameters, these are going to be the gradients and Hessians. For complex theta, you run into this terrible mathematical problem that you cannot have a complex derivative of a real function unless that real function happens to be constant. However, there is an extended sense of derivatives invented by this guy Werdinger back in the 1800s that works very cleanly. I'm not going to take you through all the details, but it's j conjugate, and the Werdinger Hessian would be hj, j conjugate, h conjugate. So these are the gradients and Hessians of the energy functional. And let's use them, and let's do some optimization. Yes? How would I obtain it? Well, so I took a year of quantum physics, and intermediate normalization often showed up in perturbation theory. So it's actually a pretty common tool for making formulas look nice.
But you would have to estimate it somehow, right?
Yes. So right now we're writing down abstract things, right? Like what they actually are kind of mathematically. And estimators will come pretty soon. Yeah. This gets better. G goes to 0, and J goes to 0 as you approach any eigenstate of H. So you get a very simple structure where you've just got the energy and you've got one part of the Hessian. OK, I have 5 minutes. How am I going to use them? I'm not going to prove that. I'm going to take you through optimization and then sampling. That's what I'll do. So gradient descent's a really easy idea. You linearize the energy difference. You get out the gradient terms, and you have a penalization term that keeps the updates small. Penalization can either be the squared magnitude of delta times some step size epsilon raised to the -1, or it can be the squared angle between wave functions, and this way is way more parameter free. It's really taking advantage of the curvature of the space. Epsilon's a tunable step size parameter. You can approximate the squared angle between wave functions using a second order Taylor expansion. You get out this fascinating matrix S, which some people would call like a quantum information metric. It encodes the curvature of the space under the parametrized wave function. And natural GD, which people all call stochastic reconfiguration in chemistry, would use basically this second order expansion plus a little fudge factor that keeps the updates small. Here's what it looks like. You choose delta to solve this minimization. It results in a linear solve in the case of natural GD, and it just results in a negative multiple of the gradient in standard GD. There's one method I'll introduce. This is maybe the last thing I have time to introduce before maybe showing you some sampling and some results. This I came up with Mike, who's in the back row, actually. I think it's really cool. We're using some second order information. So we're introducing a quasi-Hessian, which is the well-behaved one, but we're getting rid of the second derivative term. So we're doing a Rayleigh-Gauss-Newton, an adaptation of Gauss-Newton that brings in some second order information, which gets increasingly good as you approach the true ground state. As a penalization, we use the natural GD formula. Again, it's based on a linear solve. And I have some convergence theorems for the different methods. They're all based on the idea that you're getting out the parameter update by some linear solve with the negative gradient and a preconditioner matrix. The preconditioner is what really differs between the schemes. As you might expect, we can analyze this. Here's a long theorem. The takeaways of the theorem are if RGN gets applied with all of the step sizes getting bigger and bigger so you can take bigger steps, and the wave functions converging to the true ground state, energies converge superlinearly. Other methods converge a little more slowly, and it's quantified by the mismatch between PI and the Hessian. And you could see it. You could see it in practice. You can apply it to a deterministic small system where you could analyze all of these things deterministically. And you can see that, GD is pretty slow, and natural GD is a little faster. The linear method, which I haven't introduced, is about as fast as natural GD for this particular system. And then the RGN method is really the fastest. But this is a weird test, right? Because we computed all these things exactly, and in fact, you need to approximate them by Monte Carlo sampling, right? So how do you do that? That's the very last part of the slide. So I'm kind of racing. I'm sorry for that. I mistimed, but that's life. I was happy to have questions about FCIQMC. How do we estimate them stochastically? Well, we got to generate samples from the wave function density using MCMC. I mean, it'd be great if we could just generate them using independent sampling, and there are some ansatzes that permits this. But generically, if you want to sample from an unknown density and you can only do point evaluations, MCMC is the way to go. So the way MCMC works is you propose a little move from sigma to sigma prime with probability p sigma sigma prime. You accept or reject. Here's your acceptance probability. If you accept it, you move. Otherwise, you stay put. And if you do such things, you actually get samples that are drawn according to the wave function density if you do it long enough. So MCMC is powerful, but perhaps slow. You get estimators, which are empirical averages and covariances over your data. And that's the sort of thing that you would normally get from MCMC. So you can hope that these are well behaved. We've proved that they're sometimes well behaved. And in particular, from the mathematical rates, you could see that when you're approaching an eigenstate, the variance gets really small, regardless of the sampler. And you can also see that you can get lower variance in all of your estimates if you increase the number of samples or reduce your time correlations. And that last point, I just want to hark on it, because when I've implemented these methods, you really need to increase your samples. You really need to use a smart MCMC sampler that decreases time correlations. And that's just essential for achieving the best VMC energies. Sometimes it works great. So here's basically stochastic noise thrown on top of a similar convergence profile to what we've seen before. For a very large system, this is a 200 by 1 TFI spin lattice. The combination of the ansatz, the sampling, and the optimization works great for this problem. But I will end exactly on time with these limitations. In principle, from the mathematical results that I glossed over, VMC is going to converge really nicely using natural GD or especially this superlinearly converging method called RGN. In principle, right? But in practice, what everyone sees is it is just an enormous challenge to A, choose an ansatz. How did I get my ansatz? I picked the most successful example from the quantum spin literature, applied to the simplest problem, Gather enough samples. I used a ton of samples. I combined 50 MCMC samplers per core across 48 cores and performed 4,000 MCMC steps per parameter update. You know, the code was written fast, so I was able to gather all this data, but maybe, you know, with more complex ansatzes, you can't. And then lastly, when you get to huge, deep neural nets with like 1 million parameters, how do you even perform the linear algebra? This is another really difficult question. Thank you so much.